Construction produces about a third of global carbon emissions. There's a need to use materials which are eco-friendly, which have lower carbon footprint than traditional materials. Fiber reinforced polymer is such eco-friendly material which has lower carbon footprint. It requires less energy to produce than steel and other materials. Now, what is FRP? FRP is a material where we use carbon or glass fibers embedded in resin matrix. The fibers provide strength in longitudinal direction, and resin acts as a glue between these fibers. The resulting shapes resemble steel structures, and the benefit is that FRPs are 4 to 5 times lighter than steel components. And the main driver for using these FRP materials is corrosion resistance and lightweight. In today's presentation, I will present bolted and hybrid beam to column joints using FRP profiles. This is part of a conference presentation which I presented in Cape Town, South Africa back in 2022, and I absolutely enjoyed my time and I want to share my experience with you. This is how my today's presentation is organized. Firstly, I will talk about background to the research. Secondly, I will explain test setup. Thirdly, I will discuss the experimental results. And fourthly, failure modes, which are really very important in this research. And finally, I will sum up some takeaways from this research. FRP composites in civil engineering are mainly used in 3 applications: FRP profiles for new build structures, FRP reinforcing bars, FRP in repair and rehabilitation of existing structures. The research in case of FRP rebars and FRP strengthening and rehabilitation is quite well developed. However, there isn't much research on FRP profiles. And the main reason for limited research in this area is lack of understanding about joints, and there are no agreed design codes for FRP profiles. That's the reason in today's presentation I will focus on cyclic behavior of beam to column joints, where there is a very limited research on this topic. Why FRP is such a desirable material? And the main reason lies in its lightweight and corrosion resistance. And here is a real life application. This is a case study, Dawlish Bridge in Devon, UK. On your left side, you can see old rusty cast iron bridge that was constructed in 1937. Because the railway is very near to the coastal region, so corrosion is a major issue in this bridge. And on the right side, you can see FRP bridge, which actually resembles the old rusty cast iron bridge, but is very light and corrosion resistance. Even this new FRP bridge sustained 2014 storms in the UK, which were very devastating, and it is still standing as a marvel of FRP structures. The testing uses single-sided cantilever beam to column arrangement. The column is of steel material and beam is pultruded FRP. Both FRP lag angles and steel lag angles are used to connect members. Joints are both bolted and hybrid, which is a combination of bolting and adhesive bonding. You may argue that why bolting and adhesive bonding is combined in hybrid joint when the load is taken by stiff load path, which is adhesive only. There are 3 main situations when hybrid joints are very useful. Hybrid joints can resist load in all directions. Bonding is good in shear, and bolting is really excellent in tension and transverse loading. So combining them, we can utilize the useful, desirable properties of both materials. Fire and long-term fatigue performance of hybrid joints is better than bolted or simply adhesively jointed joint. However, the extra cost of fabrication must be carefully weighed against the benefits of hybrid joints. This slide shows joint detailing. 6 tests are conducted. First joint uses bolted steel flange and web cleats, and it has hybrid version with both bonding and bolting combined. Third and fourth joints are similar to first and second joint but without web cleats. Finally, fifth joint uses FRP flange and web cleats. Loading protocol. Now this is very interesting. In the absence of ductility, finding a suitable loading protocol was a bit of a challenge for us. We reviewed loading protocols for steel, timber, and non-structural elements. As most protocols were based on steel yielding, we decided to use SAC loading protocol, which is based on displacement. And here you can see number of cycles versus axial displacement. That is how we applied loading to the specimen. Test results. Joints with steel web and flange cleats. These are moment rotation, hysteresis curves or loops. Left curve is for bolted joint and right curve is for hybrid joint. Monotonic curves are shown by dashed lines and cyclic curves are shown by dotted lines, and backbone curves by solid line with markers. It's interesting to note that bolted joints started to show damage at about 2 kN meter and hybrid joints showed damage at 5 kN meter. Hybrid joints certainly delayed initiation of damage. Hybrid joints showed at least 50% higher moment and stiffness than companion bolted joints. These are test results for joints with steel flange cleats only. These test results are almost identical to joints with web and flange cleats. The moment capacity and stiffness are almost the same. Here we are reaching an important conclusion. Web or flange cleat on its own is enough to resist applied load. So which means that we can only use web cleat or we can only use flange cleat. There is no need to combine them both. However, robustness of the structure should be considered when we are using flange cleats because the joints can rotate in out of the plane direction. These are test results for joints with FRP, web and flange cleats. Other 4 tests that I mentioned earlier, they used steel cleats. It is important to note here that both moment and stiffness is far lower as compared to steel cleated joints, which is quite obvious because when we use FRP cleats, the failure can be due to delamination and cracking, which I talk about little later. What is the cyclic performance of beam to column joints? And this is really very crucial because there isn't much research done on earthquake resistance or cyclic performance of beam to column joints, which is really very important area. In this graph, accumulated dissipated energy is plotted. How do we plot this energy? This has been plotted as area under moment rotation curve for each joint. Dashed lines here show hybrid joints and solid lines show bolted joints. Blue lines are joints with steel and flange cleat and gray lines show only flange cleated joints. Joints with FRP cleat showed the worst overall performance in terms of dissipated energy, and this is pretty obvious from this graph. However, there are no differences in flange and web cleated joints compared to flange only joints, and the reason is that flange or web cleat on its own is sufficient to resist the applied loading. Hybrid joints showed as much as 75% more dissipated energy than bolted joints. Dissipated energy of FRP cleated joints is about half that of steel cleated joints. There were 3 main failure modes that were observed in this research. First failure mode is shear failure of beam's bolted zone. The specimens with bolted steel cleats showed this failure where the bolts are trying to shear out of the beam. This type of failure happens in plate-to-plate connections with short end distances or when fibers are oriented in the tension direction of the force. The second failure mode observed was adhesive debonding with shear out failure. And this failure happened in hybrid joints with steel cleats. The failure started with adhesive debonding followed by shear out failure of beam's bolted region. Some cracking at the web flange junction of the beam was also observed in this failure mode. Third and final failure mode is delamination cracking, and this happened when we used FRP cleats. And the failure mainly happened due to delamination cracks at root radius of FRP cleats. However, no cracks were observed on beam side. Now this is quite obvious when we use softer materials like FRP as cleats. When you apply a moment, first thing that will fail is the weaker material or weaker component, and that is FRP cleats. That is the reason we observed a lot of cracks, as you can see in this picture, and the specimen failed due to delamination cracking of cleats. Now I'm in a position to conclude the work. There were three main failure modes observed in this research: shear out failure of the beam's bolted zone, adhesive debonding with shear out failure, and delamination cracking at the root radius of FRP cleats. Hybrid joints were much stiffer than bolted only joints. Accumulated dissipated energy of hybrid joints is about 75% higher than companion bolted joints. Energy of FRP cleated joints is about half the steel cleated joints. Web and flange cleated joints compared with flange only cleated joints showed no difference in results. Adhesive bonding delayed the initiation of cracking. Currently, our research group is working on PFC RHS and RHS RHS beam to column joints. PFC is parallel flange channel, RHS is rectangular hollow sections. These are practical joints which have been used in industry for quite some time, but there is no research available on these joints to back up their behavior. The first joint, which is PFC to RHS joint, it has been used in railway platforms quite a lot. Second is RHS to RHS joint, which has been used by Creative Composites USA in their cooling tower system. These are few references which I used for preparation of this presentation. The first journal paper is our paper in composite structures, which is on monotonic testing of same joints, and I presented some of the work initially here as well. Thanks for listening. I know this is not the real audience, but if you have any questions, put them down in the comments. I'll be able to respond. A recent review paper which is on FRP composite structures, it is mentioned over here, and it is becoming really very popular with lots of citations, and you can contact me on these contact details. The presentation will be available at bit.ly/SEMC 2022-JQ. You can download the presentation from there. And thanks for your time. I will see you in my next presentation.